Well, hello, calculus students and seekers of truth. In this video, in this lesson, we will learn a numerical approach to solving or estimating solutions for differential equations. So it's something called Euler's method, and it builds on this idea of linear approximation. So let's review a little bit and then get to the specifics. So if you have some function f of x where you happen to know that there's a point on there, 3, where the y value is equal to 5 and the slope is equal to 2.5. So we can write it up as such, right? So let's say you have an xy plane. There's some sort of curve here. We know that this point here exists and it is 3, 5. And we also know at the same time that there's a slope, or the tangent line that goes through here has a slope that's equal to 2.5. And so writing the equation of this line is fairly straightforward. We can say that the equation is y equals, and I'm going to use a kind of a point slope form version of this. The slope, which is 2.5, multiplied by x minus 3 plus 5. Okay? So that tells me that it's going to go through the 0.35, or shift it over from 0, 0 to 3, 5, and it has a slope of 2.5. And we're going to use this line to estimate the value of f of 3.1. So f of 3.1 is pretty close to y of 3.1. So we put this information in, put 2.5, 3.1 minus 3 plus 5, and we get a total that's 1/10 and times 2.5, so 5.25. Right. And again, what this means is that when x is equal to 3.1, the value on the tangent line is very, very close to the value that's actually on the curve. Now, if we extend this idea to something like in this example, we're going to use a differential equation. dy dx is equal to 2x plus y. Y is equal to f of x, and find a solution that for a specific solution that passes through 1, 2, estimate the value of f of 2. Okay. Now, we would have a pretty hard time solving this differential equation using separation of variables because of this addition, actually, subtracting y and adding 2x or subtracting 2x, we are not able to cleanly separate the variables. So we can employ this method of linear approximation in the following way. We know that the slope of this curve at the point 1, 2 is going to be equal to 2 times the value of x plus the value of y. So that gives me a grand total of 4. And that means that the tangent line, and I'm going to call the tangent line here L of x, is going to be equal to a line with the slope of 4 passing through 1, 2, so shifted 1 to the right and 2 up. And then if we want to estimate the value of f of 2, right, so we know then that the value of f of 2 is approximately equal to the value of L of 2, which is 4 times 2 minus 1 plus 2, which is just going to give me 6. Okay? So using this tangent line that passes through the point 1, 2 to find the value of f of 2, we get about 6. Okay. Now, what we have here is a slope and a point, and we're able to find an equation of a line. But one of the things is that the point 1, 2 here, or x equals 1 versus x equals 2, they're pretty far apart from each other, relatively speaking. So the estimation here from 1 to 2 might be pretty inaccurate. If you look at the previous example, we're using f of 3 to estimate f of 3.1, so we're going to get a better estimation. But what if we are in a situation like number 2, or the second example here, where the point where we have and the point that we're estimating is a little bit farther apart? Okay, so it could get pretty darn inaccurate. So I'm going to introduce a new idea here. Well, rather, it's not my idea. It's Leonard Euler's idea. It's called Euler's method, where we're going to repeatedly do linear approximation until we get to the right answer. Okay, so let's let me articulate what we're doing first, and then we'll actually see an example. So given a differential equation, dy dx, that's generally something difficult to solve algebraically, right? If it was easy to solve algebraically, we would just do it that way. And given a point that's on the specific solution, so kind of like this one right here, 1, 2, the equation dy dx, we want to find a numerical estimation for a specific solution, and we're going to use, again, what's called repeated linear approximation. Okay, so we're going to take this process that we did up here and do it a bunch of times. Okay? And we're going to increase, instead of increasing by one full unit every time, we're going to increase it by a smaller fraction or a smaller length. And whatever that increment is, we call that a step. All right? So I'm going to end this video here, and then we're going to start another one where you see this particular example in action. As always, thank you for watching. Ask for help if you need it, and have a wonderful day.